tell from the perspective of this carbon first, you can identify, right? H and 2 carbon, right? CCH, right? What about this one? You will have 2 hydrogen, right? And carbon, so this is HHC, right? So this one should win the upper one. And then on the opposite side, so this is also isomer as well. Right? So 1 and 2 probably answer. 맞죠? 그래서 같은 레벨에서 비교를 해보시고 세 개의 원딩을 거기서 하나라도 더 higher priority element을 포함하고 있다. 그러면 걔가 이기는 거죠. 거기까지 동률이다. 그러면 그 다음 레벨로 내려가서 비교를 했을 때 higher priority element를 가지고 있다. 그럼 이제 그 차원에서 이기게 되면 결국에는 그 substitut가 이기게 되는 거다. 그렇게 적용을 하시면 되겠습니다. 그렇죠? Okay. Yes, we can check the answer for this one as well. This is for chapter 3, I guess, conformational state. So probably you can solve the upper one A, B, draw the most stable choke conformer of cis, right, versus trans, 1 ethyl, 2 methyl cyclohexane. So you can draw, right? The first conformer you can think of and assign 1 and 2. So maybe you can this carbon is 1, this carbon is 2, and 1 ethyl. And you can first think about, right, this ethyl goes through the equatorial position. Right? So this is one possibility. Right? And since this ethyl is equatorial, that means this substituent is attached to the outside, right? Respect to this carbon. And in order to be cis, right, then here at 2 carbon, you have to have down methyl, right? So down methyl, for cis has to be up methyl, right? So this is to be this methyl, ethyl there. That's one possible conformation or a conformation state for cis, right? So 1 equatorial, 1 axial. Right? That's for cis. And you can also think about the ring flip version of that. Right? You can do ring flip. You can draw the flip skeleton structure for a chair. And still, right? This is number 2 carbon. This is number 1 carbon. Okay? And then at 1 carbon you have ethyl moiety set up, right? And this carbon is up. You can have ethyl moieties here. And at number 2 carbon you have up methyl, but this is now the down carbon. So up should give you an equatorial methyl, right? So the axial methyl goes to equatorial methyl, and also the equatorial ethyl goes to up ethyl, the axial ethyl after ring flip, and you can compare which one is more stable. It looks comparable, but the larger substituent ethyl is here in the left-hand side, located in equatorial, so probably better. The ethyls just here in an axial position, and 1,3-dioxane traction give you destabilization more than as methyl does. So that's probably the more stable conformer from cis. What about trans, right? You can try to identify the initial conformer from this skeletal structure first. And still you can identify this is 1, this is 2 carbon, and try to locate ethyl at the equatorial, right? And again, this is the down carbon's equatorial, meaning this is the up, right, substituent. In order to be trans, right, then substituent attached to 2 has to be down. And you can then draw methyl equatorial, right? They're going to be down substituent. Right? So up and down satisfying trans. now you're seeing, right, two substituents, both substituents are at the equatorial. So have this right, complement. If you can imagine after ring flip, you can draw by yourself ring flip. Now these two equatorial will go both axial, right? What is the worst case? This one has to be the more stable chair complement. And you can generalize this trend to the bottom case, right? So bottom one is asking you for each of the following cyclohexane indicate the disubstituted cyclohexane indicate whether substituting two chair complement will be both equatorial in one chair complement and both axial in other, or one equatorial and one axial in each of the chair complements. So you can identify, right, for each case. This case or so both equatorial or both axial, or one equatorial and one axial, right? And you already saw, right? Cis 1 and 2 versus trans 1 and 2, right? So trans 1 and 2, you know that this case or both, right? You have both equatorial, and if you do ring flip, you'll get both axial, right? So that was the trans. But cis, you've already seen, right? One equatorial, one axial for both complements. This is 1/1. Right? What about the other case? And you can draw one by one, but you can identify a pattern here. Right? If you're switching just one number, then that will give you the inverted trend. Or if you switch cis versus trans character, that will give you inverted trends too. In some slide, cis 1, 3 will give you both. Right? Sorry, changing both. So you're switching from here cis 1, 2 to cis 1, 3. So this will gonna be both actual, but you can draw and double check. Okay? So you can assign maybe here 1, 2, 3, or the same way. 1, 2, 3, and draw cis, right? So for cis, you can start with one substituent on the equatorial, maybe. So substituent 1, right? And then this must be then up. This is the equatorial for the down carbon. So this is the up substituent. Then in order to be cis, right? The substituent attached to here, this number 3 carbon should be also the up substituent. And this is down. So down carbon. So it's go through the equatorial as well. Right? So both equatorial. And then if you think about the ring flip version of that, then you will get both axials as well. So this is both case. 연습이 안 되신 학생들은 제가 지금 이렇게 추격해서 설명드리면 아마 못 따라오실 거고, 연습이 충분히 되신 학생들은 아마 이미 무슨 말 하는지 다 알 텐데, axial, equatorial, ring flip 이런 것들 익숙해지셔야 됩니다. 그래서 그냥 첫 봐도 이제 마스터가 되시면 그냥 바로 아실 수가 있게 될 거예요. 그래서 위에 문제를 풀고 나면 밑에 문제를 이제 저희가 제너럴라이즈 할 수 있는 건데, cis 1, 2, trans 1, 2는 이제 위에 A, B 풀면서 저희가 패턴을 확인했고, 이제 오른쪽 4개 cis 1, 3, trans 1, 3, cis 1, 4, trans 1, 4는 이제 어떻게 되겠느냐. 컨포머를 그리면 하나는 axial, 하나는 equatorial, 항상 얻어지는 구조로 나오냐, 아니면은 뭐 하나의 컨포머에서는 both equatorial 혹은 ring flip 되면 both axial로 되는 두 가지 중에 어느 것에 속하냐라고 물어보고 있는 거예요. 이제 하나씩 다 그려보시면서 연습해 보시는 걸 추천은 드려요. 아직 감을 못 잡으셨으면. 근데 이제 발견하실 수 있는 규칙은 이제 cis 1, 2는 하나하나라는 걸 알고 있죠. 그리고 trans 1, 2는 both라는 걸 알고 있죠. 그럼 여기서 이제 패턴이 trans에서 cis로 바뀔 때 숫자가 하나씩 바뀔 때 이제 어떻게 바뀌게 되는지 한번 본인 스스로 그려보시고 both의 케이스인지 1 and 원 케이스인지 한번 구별을 해보시기 바랍니다. 그래서 지금 DEF도 하실 수 있겠죠? 그래서 한번 해보시고 답을 한번 스스로 구해보신 다음에 일반화를 한번 시켜보시기 바랍니다. 그래서 뭐 일단 하나의 컨포머를 정해서 그리시고 그 규칙에 맞게 그려보신 다음에 윙플립을 그냥 해보면 되겠죠. 일단은 이퀴토리얼이든 액츄얼이든 본인이 정한 기준으로 하나의 서브스턴트를 이퀴토리얼을 그리든 액츄얼을 그리든 거기에 맞춰서 시스라면은 같은 업사이드 혹은 다운사이드로 하게 그리신 다음에 이게 이퀴토리얼의 두 개가 다 있는지 아니면 하나는 이퀴토리얼 하나는 액츄얼인지 그걸 구별하시면 되겠죠. Okay, so you can generalize, but for each one you can test one by one for sure. Right, that was the P set. Then I guess we were kind of like in the middle of this. We were in the middle of discuss the isomers containing asymmetric centers, and we define asymmetric centers. The carbon side, where carbon had 4 different substrates, right? And this will give you a very important treat or characteristics. That's what we can review here. And we define chiral versus achiral molecules, and this can apply to any general object as well. If you have a object here, like lecture10, for instance, and then you can draw right a mirror image. You can imagine there's a mirror in the middle, and you can draw right mirror image of any object. And if these two are superimposable, then you can define, right? You can call out this object, given object as chiral or achiral, right? In the case of left hand and right hand, so mirror image to each other, they are non-superimposable. That's why this is chiral species, right? Or chiral object. So although everything is a mirror image, we can imagine mirror image may or may not be superimposable to each other. Some molecules, you can think about molecules here too. So some molecules are like hands, left and right hands are mirror image, but they are not identical or superimposable, in other words. In this case, you can call out as a chiral. Achiral molecules, if two mirror images are superimposable or identical, then you can call it as achiral. Right? And we discussed root, right? Chiral in hand root, so you can say right-handed or left-handed molecules. That is asking you about stereochemistry. Chirality check, very easy. Following just the definition, you can draw the mirror image of a given molecule. And if these two are superimposable, then it's achiral. That's why water is achiral. What about this CH2BRCl molecule? They do have same CH bond, right? In this case, you can apply the definition again. So you can draw the mirror image of this and check whether these two are superimposable. In this case, superimposable, right? That's why this molecule is also achiral. Okay? 그래서 chiral achirality의 이제 가장 상위 데피니션은 mirror image를 그리시고 그 주어진 오브젝트와 완전히 겹쳐진다, 포개진다, 아이덴티컬하다. 그러면 이제 achiral. 그리고 그렇지 않다. 그러면 chiral. 이렇게 정의를 할 수가 있다고 말씀드렸고, 근데 이제 분자 구조가 조금이라도 복잡해져요. 그렇죠? 카본이 여러 개 있는 구조라든지 컴플렉스한 모레큘을 다루게 되는 경우에는 미러 이미지를 언제 다 그려보고 언제 슈퍼임포즈 된지 어떻게 체크해요? 만약에 본인이 엄청난 그 공간 지각 능력이 있어서 머릿속에서 회전이 되고 이 컴플렉스한 구조가 전부 다 머릿속에 한 번에 들어오면 가능할 수도 있으나 불편하죠. 그렇게 할 필요가 없고, 이제 achiral center, 뒤에서 얘기하겠지만 asymmetric center라는 개념을 도입함으로써 쉽게 chiral, achiral 분자냐를 이제 저희가 판별할 수 있게. Okay? So this is how you can check the chirality. This can apply to simpler molecules, but you can imagine, right? You're dealing with very complex structure, complex molecules. Then checking all of this for that complex structure is very, very cumbersome. Okay? So we need to define some useful tool or useful properties here. So before getting into the asymmetric center, you can also think about the plane of symmetry. This is pretty general features, like for the A-chiral molecule. A-chiral molecule usually, not always, but usually, in most cases, contain plane of symmetry. So CH2Br, the molecule just saw in the previous slide, it has the plane of symmetry. Okay? If your molecule has this kind of like plane of symmetry, the tonal symmetry plane, then most cases has to be achiral. Okay? Cause of chirality. Now we are defining in the slide asymmetric center. With one asymmetric center, the molecule will always be chiral. Because these features, the fact that the molecule has a single asymmetric center will give you the non-superimposable mirror image. So take this as an example, right? And you can draw the mirror image of that. And these two never get superimposed, right? Meaning this molecule has to be chiral, right? And you can define here the asymmetric center, or also called the chiral center, right? Atom bonded to 4 different groups. So if you can identify a carbon that have 4 different substituents with respect to the central position, then this central position is called asymmetric center. And if your molecule has one single asymmetric center within the structure, then that molecule always be chiral, right? But if your molecule have 2 or multiple asymmetric centers, then you have to think about a little bit further. Okay. The carbon atom with 4 different groups is also called the tetrahedral stereogenic center. So we'll define stereogenic center, which is not necessarily identical to the asymmetric center. We'll distinguish these two in the subsequent slide. But for now, you can think about it, almost identical one, right? So you can identify here this carbon, and this carbon. They do have 4 different substituents. That's why they have star on it, right? And because these 3 molecules have one single chiral center, asymmetric center, this molecule is chiral. Okay? You can rationalize why this carbon has 4 different substituents, of course. You can locate asymmetric center. You can examine each tetrahedral carbon in a molecule and look at the 4 groups, the 4 atoms bonded to it. Okay, and there are some general features you can remember. Always omit from concentration. All carbon atoms cannot be tetrahedral stereogenic center. This includes like CH2, CH3 groups. Right? It's obvious this carbon has 2 hydrogen. Right? This carbon is 3 identified hydrogen. They cannot be asymmetric center in the first place. Or any sp or sp2 hybridized carbon, they cannot be asymmetric center. They cannot accommodate 4 groups, right, in the first place. So this is an example. We'll define stereogenic versus asymmetric center in a few slides later. For now, you can think about this asymmetric center. It's identical to the stereogenic center. This has 4 different groups, of course. So the center of carbon is asymmetric. In this case, you can take an example here. Also, the larger organic molecules can have 2 or 3 or even hundreds of asymmetric centers. In this case, right, you have 1, 2 asymmetric centers. This one also has 2, right? What about this one? You have 3 asymmetric centers, right? So one single molecule can accommodate multiple asymmetric centers. And we, I guess, solved this one. How many asymmetric carbon exists for this molecule? Drop used to treat Parkinson's disease. And I guess we checked the answer here. This carbon, and this carbon has 4 different substituents, 4 different arms, in other words. So answer is 3. You can double check either one of these. You can simply cross out this CH2, CH2, CH3 moieties, right? And this 2. Well, this cannot be asymmetric center. It has more than two identical groups, right? Which is hydrogen in this case. sp2 carbons, right? And CH2 cannot be asymmetric centers too. And here cannot be asymmetric center as well. sp2, 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 and sp2, so they cannot be asymmetric centers. So after crossing out all these possibilities, then you should be able to identify these three. Okay? Right, and we can think about the chirality and asymmetric center a little bit more, the relationship between chirality and asymmetric center. And as I mentioned, with one single asymmetric center within the molecule, then that molecule will always be chiral. That's a true statement. Okay. With two or more centers, molecules may or may not be chiral, right? That's what you should remember. In general, molecule with no asymmetric centers will not be chiral, but there are some exceptions. As yellow highlighted. This molecule, right, below, the yellow highlighted one, they're all chiral molecule, but they don't have asymmetric centers. So there are exceptions to that. Okay? Molecule with no asymmetric centers, generally speaking, they will not be chiral, but these are exceptions. Okay? 그래서 뭐 아주 일반적인 경우만 따지자면 asymmetric 센터가 없다. 그러면은 카이랄하지 않을 확률이 높죠. 그렇죠? 근데 exception이 있어. 이런 알렌이라고 부르는 모lecule이나 아니면 바이넨, typical example인데요. 이런 모lecule들의 경우에는 이제 카이랄리티를 띄고 있음에도 불구하고 asymmetric 센터가 없습니다. asymmetric 센터가 없는 분자라도 카이랄할 수 있다. exception은 존재할 수 있다. 이렇게 기억해 주시면 될 것 같아요. Number 4, a chiral molecule usually, right, as I mentioned earlier in the slide, usually contain the internal plane of symmetry, but chiral molecules do not. This is a general statement, but there are still the exception to this as well. As you look down this, right, the blue highlighted case, this is still the a chiral molecule, but doesn't have any plane of symmetry. This is the molecule, they don't have the plane of symmetry, but this is the a chiral molecule, right? So there are exceptions to number 4. 그래서 대부분의 경우 a chiral molecule이면 internal plane of symmetry가 있다라고 이제 보통은 이야기를 하는데 항상 true statement은 아니다. exception이 존재하는데 exception에 해당되는 이제 특이 분자를 밑에 제시해 놓은 거죠. 그렇죠? 그래서 A structure 같은 경우를 가지고 이제 rotation 90도 하고 reflection을 한번 하면 결국 같아지는 구조가 나오는데 이것이 이제 특별한 example이죠. A 같은 경우에 plane of symmetry 4번 exception에 되는 케이스가 된다. 그래서 일반적으로 3번, 4번 general statement라고 이야기를 할 수 있으나 100% true는 아니다. 이 정도로 이해하시면 되고 OChem 1 코र्스 정도의 스코프에서는 사실 exception 정도를 크게 기억을 안 하셔도 크게 무리는 없으나 이제 100% 맞는 스테이트먼트는 아니다라는 것입니다. 3번, 4번의 경우에는 exception에 해당되는 분자가 있고 그러면은 카이랄리티를 어떻게 또 더 리버스하게 정의하느냐 나중에 무기화학 수업 시간에 분론을 배우는지 모르겠어요. 저희 학부에서 제가 무기화학 수업은 하진 않는데 관심 있는 학생은 화학과 수업을 들을 수도 있고요. 더 정확한 시메트리 팩터에 대해서 공부를 하게 되면 거기서 카이랄리티를 조금 더 리버스하게 정의를 하게 되는데 저희 수업에서의 범위는 좀 넘어가는 것이고요. 일단은 1, 2, 3, 4번 제너럴 스테이트먼트에 대해서 이해를 하시고 받아들이시면 되겠고 exception 정도가 3번, 4번에 있을 수 있다라고 정도 이해하시면 될 것 같습니다. Okay? So again, number 1 and 2 are correct statement. Okay? Number 3 and 4 generally true for many of the molecule, but there are exceptions to that. Okay? Right. So the easiest case, isomer with one asymmetric center. Right? And as we discussed, if your molecule has one single asymmetric center, then it is chiral, right? And you can think about the isomers, right? Within that framework. So molecules that are they are non-superimposable mirror image of each other. They are called enantiomer, right? So in this case, you can identify the asymmetric center on this carbon. It has 4 different substituents: hydrogen, methyl, bromel, ethyl groups, right? And then you can draw one enantiomer, right? And then you can draw the mirror image of that enantiomer, right? These two are called enantiomers to each other, right? 2 stereoisomers of 2 bromobutane, right? These two are called enantiomers to each other. So 한국어로 굳이 번역을 하면 거울상 이성질체라고 표현을 해서 아마 이제에서 배워봤을 겁니다. 그래서 이시메트릭 센터가 하나만 있는 분자의 경우에는 이제 거울상 이성질체가 생길 수 있다. 그렇죠? 카이럴한 분자고요. 앞에서 정의한 이제 스테이트먼트에 의해서 넘버 1 스테이트먼트에 의해서 카이럴한 분자고, 카이럴한 분자는 거울상 이성질체를 가질 수 있다. 이렇게 이해하시면 되겠죠. Alright, then how to draw the enantiomers, right? There are the perspective formula that you should stick to, right? And there are some rules, right? How to draw solid wedge, half wedge, right? And this is the perspective formulas of the enantiomers, right? These two are the enantiomer to each other. And you can identify this notation versus this notation, right? This notation is called the solid wedge, and this notation is called half wedge, right? Solid wedge represents, right, the bond that extends out of the plane, out of the paper, right? So it's protruding to your viewpoint, right, towards your eye, basically. And then you can think about this half wedge. This represents a bond that points backward, okay? Back from the plane of your paper, away from the viewer, right? So that's how you can represent these 3D structures. And this normal single bond, meaning these 3 items, 3 entities are in the plane, the paper in other words. Okay? This and this protruding out and in from the plane. That's how you can read and draw the perspective formulas. Okay? And then you can draw the mirror image to that, right? With respect to the mirror in the middle. Then you can rationalize how this can be an enantiomer from light. Okay? So when you draw a perspective formula, you should make sure that 2 bonds in the plane, these 2, right? The paper are adjacent to one another. And these 2 has to be adjacent, right, to each other. That's a rule you should stick to. Right? You cannot draw, for instance, like this. This is not allowed for the perspective formula. You have to locate these 2 are on the adjacent side. Or you can also think about it this way. Right? These 2 has to be sitting next to each other. These not allowed. Okay? That's what this statement is all about. So neither the solid wedge nor the half wedge should be drawn between them. That's what. This is not allowed. And when you draw the first enantiomer, the 4 group bonded to the asymmetric center can be placed around in any order. You can pick any order in random orders, right? And then based upon that given perspective formula, you can draw the mirror image to that, or second enantiomer, by drawing the mirror image, right, of the first enantiomer. So you can draw this first, and then imagine there's a mirror in the middle, and then draw the mirror image. Then that'll give you the second enantiomer and perspective formula. Okay? So you can practice here, draw both enantiomer. You can first draw the first enantiomer, right? In using this normal bond and half wedge and then solid wedge to indicate, right, the studio location. You can identify A first, right? And then just draw the mirror image to that. You can imagine there's a mirror in the middle, and just draw, right, the mirror image. That will give you B. Okay? That's how you can draw those enantiomers. There's a little tip to draw a second enantiomer based upon the first enantiomer. So let's say you have this first perspective formula for the given enantiomer, then you can switch just to interchanging two of the atomoi group, then we give you, right, the second integers too. Okay? So in this case, you can imagine these two swapping this two, right? This will give you this, right? And this will formulate the enantiomer from the left. So that's a simple trick you can think of, right? So you're going to need to draw mirror in the middle, okay? And draw literally the mirror image to A. You can do that for sure, but you can do also the bottom one, bottom two, just exchanging two, right? Then that will give you and then formulate the second enantiomer. 그래서 뭐 가장 직관적인 방법은 퍼스펙티브 포뮬러로 하나의 이니셔얼을 그리시고 그다음에 가운데 미러가 있다라고 생각하신 이후에 정말 리얼리 미러 이미지를 그리시는 방법이 있겠죠. 그리고 세컨드 이미지로 완성될 수도 있으나 나는 그렇게 하는 건 싫다. 그렇죠? 뭐 싫을 수도 있죠. 그러면은 바텀 팁을 사용하시면 됩니다. सब스트레이트 두 개 그냥 스위칭만 하시면 그 전 구조에 대한 이니셔얼가 나옵니다. 그거는 왜 그런지 본인이 한번 머릿속에서 그려보시면 쉽게 이해가 되실 겁니다. So you can choose either drawing literally the mirror image from one to the other, or you can treat the bottom, just exchanging two substituents from the original nature, and then give you a second nature. Okay, this is the additional example. You can tell, right, this and this, that asymmetric center and this two are enantiomers of each other, and the same is true for this case. There's one another way you can present the enantiomers or identify the stereochemistry of the molecule. So this is called the Fischer projection, right? And here you can identify the cross, right? Here and there, and in the middle, right, you have a carbon, and this carbon is the asymmetric center. This has 4 different substituents, right? That's why the center, this carbon is asymmetric center, and you should understand what this cross, right, is telling you. This represents asymmetric center as a point of the intersection of the two lines, as I mentioned. The horizontal lines project out, okay? 2 and 4 in this case. It projects out the plane of the paper toward the viewer, okay? And the vertical line 1 and 4, right, extend back from the plane of the paper, away from the viewer, in other words, right? So you can think about then, when you read this Fischer projection, you should be able to draw this 3D presentation in your head, right, using this. Right? So this Fischer projection is again equivalent to this 3D presentation of solid attachment match. 2 and 4, again projecting out of the plane and towards your eye, the viewer. The vertical line extends back from the plane, out of the paper, away from the viewer. Okay? That's how we can read the 3D architecture, 3D structure of the molecule containing asymmetric center. When you draw an enantiomer using Fischer projection, you can put 4 atoms or group bonded to asymmetric center in any order that you did for the perspective formula, right? And then when you draw the second enantiomer, as I mentioned, you can simply interchange 2 of the groups, right? Does not matter which 2 you interchange. This will give you the second enantiomer. Right? So in other words, you can change any 2, right, substituents and switching. For instance, in this case, 1 with 4, that will give you a second enantiomer. Okay? Or 1 and 3, 2 and 4, 1 and 2, everything is fine. Okay? Just interchanging 2 of the groups, that will give you a second image or enantiomer. Okay? And you can practice this one, right? Draw enantiomer for perspective formula and Fischer projection for each case, right? So you can draw both enantiomers, like perspective formulas and Fischer projections. Okay? 약간 기본적인 내용이지만 잘 숙지하셔야 됩니다. 채점할 때 보면 아쉽게 정말 이런 거 한두 개 실수해서 풀 크레딧 못 받는 학생들이 정말 많아요. 그래서 연습을 좀 하셔서 잔실수가 없게 숙지를 하시기 바랍니다. 본인이 약간 이쪽에 아직 익숙하지가 않다 그러면 제안하는 공부법은 이제 퍼스펙티브 포뮬러를 그리시고 피쉬 프로젝션을 그리신 다음에 두 개를 같이 매칭시키는 거예요. 그렇죠? 처음에 익숙하지 않은 학생들은 각각의 쓸기 구조가 나타내는 것을 이제 머릿속에 좀 그리시는 거 연습을 하셔야 될 겁니다. 그리고 조금 익숙해지면 머릿속에 이제 패턴화가 돼서 실수가 없으실 거예요. Okay, so maybe we can take one as example here. You can identify first, right, the asymmetric center. Obviously, this carbon is the asymmetric center, has like hydrogen, bromo, methyl, and the small a's, right, containing alcohol. Okay, and then you can perhaps identify, right, these two in the plane, but that's asymmetrical. And then you can draw solid wedge and hatched wedge, right, to indicate the stereochemistry. Right? This is one possible perspective formula for the one enantiomer. And then you can draw the second enantiomer, just literally drawing the mirror image to that. That's one way. Or you can simply exchange, right, two substitutes. You can exchange this. This will give you the second enantiomer, right, from the upper one. But these two are the enantiomer relationship. Of course, you can draw, as I mentioned, here we're drawing the mirror image. That works too. Okay. These two will formulate two enantiomers, but these two are identical. You can double check by yourself. Okay. You can apply the Fisher projection here too, and you know that this is the asymmetric center, right? And then just locate any four substitutes in any order, right? So you can put H, methyl, bromo, and alcohol. Right? That's one enantiomer you can think of, and then you can simply swap any two substituents that will give you, right, the enantiomer. Of course, you can just draw literally the mirror image to this, right? As you can imagine, there's a mirror in the middle, and you can just draw mirror image to that. This will give you the mirror image, the second enantiomer, or as I mentioned, you can just simply swap this too. This and this in an enantiomer relationship, and that means this and this has to be identical. That's another way you can draw. Okay, you can do the same thing for 2 and 3. But my suggestion here is to, if you are not familiar with this, right, you can draw the perspective formula one by one and try to match that one the correct Fisher projection to it. Right? That's how you can cross-check the perspective versus Fisher projection for same 3D configuration. Right? That's how you can draw the 3D architecture in your head. That was what we're supposed to finish the last lecture, and then we can move on to lecture 10. Okay, so yeah, so some you made your thesis, but the homework set is uploaded now on TL, so you can try to solve and submit to submit on midterm exam day. You should bring the hard copy of your solved the PSET and submit to the TA before the exam starts. Okay, that's the due date and time. Check the ETL. This is the last year's midterm exam, as I mentioned. So you can get a sense how the exam is going to be. Okay. And game 2 is the exam day, the midterm exam day. And before exam start, you should submit to the TA, the proctor, the exam. Okay. 그래서 homework 1이 업로드가 됐고요. 그거를 이제 푸셔서 중간고사 날 가져오시면 돼요. 하드 카피로 가져오시는 게 원칙이에요. 그래서 그거를 까먹고 안 가져오시는 학생들이 좀 있어요. 까먹지 마시고 푸신 숙제를 가지고 시험 감독을 할 TA들에게 시험 시작 전에 제출하시면 돼요. Okay? Alright, so we are still on the isomers. I guess we are discussing the stereoisomers, isomers that contain asymmetric centers. That's what we are studying here. And yeah, so as I mentioned, here we are comparing, distinguishing the asymmetric center versus stereogenic, which are similar but not identical. Okay. First, you can define. You know asymmetric center. What is asymmetric center? It's a carbon site containing 4 different groups. That's how we define asymmetric center in the previous slide. Stereogenic center, on the other hand, is defined as an atomistic site. Atomistic site or atom at which the interchange of 2 groups produce stereoisomers. Cis versus trans, or R versus S, or in other words, 2 different managers. This is how you can define the stereo center, which is the definition is different from the asymmetric center, which are related but not identical. Okay? By the difference, right, in definition, there are some relationships arise. Right? Both asymmetric center, right, where the interchange of 2 groups produce an enantiomer, and 2, the sp2 carbons of alkene or sp3 carbon of cyclic compounds, where the interchange of 2 groups converts cis isomer to trans isomers or vice versa. They can belong to stereo centers. Okay? So asymmetric center, they can be called out stereo center because interchange of 2 groups will give you, right, different enantiomer. We'll learn about this later. This will give you R to S, S to R conversion. Okay? What about 2? The sp2 carbon of alkane or cyclic compound. The sp2 carbon of cyclic compound, if you interchange 2 groups, that'll give you cis to trans, or trans to cis isomeric conversion. These 2 cases, right, you can call out stereo center. Okay? Then you can think about the relationship between the asymmetric center versus stereo center. Right? The asymmetric center, right, the molecule containing asymmetric center can be called, right? They can also have a stereogenic center, right? So here, for instance, you have the asymmetric center, the carbon site, and 4 different substituents, right? In this case, switching, right? Swapping 2, right? One from the other, right? Will give you the second enantiomer, right? That's why this asymmetric center can also be called out as stereo center, right? And as we define above, right, this sp2 carbon, right, switching, right, substituents, let's say these 2, right, hydrogen versus ethyl, will convert cis to trans, right, E to G, right, conversion. That's why this center can be also called out the stereo center. But this carbon is not the asymmetric center, right? So then you can say all the asymmetric center is a stereogenic center, but not the vice versa. What about this? The carbon, sp3 carbon in cyclic compound, right? You can swap to change cis versus trans character too. So that's why this center can be called out the steric center. But you cannot say this carbon has asymmetric center because this carbon has identical, right, substitutes, right, two substitutes. This is not the asymmetric center, right? So again, you can say all asymmetric center can be a stereo center, right? But not vice versa. You can think about this Venn diagram relationship. Then you can count, right? How many asymmetric center does the following compound have? Right, this one. B, how many stereo centers does it have? You can distinguish, right? Asymmetric versus stereo centers. Follow the definition. 그래서 stereo center와 asymmetric center의 이제 엄밀히 말했을 때 definition이 다르다라는 걸 인지를 하고 계시면 되겠죠. stereo center는 어떤 atomistic 사이트예요. 분자가 가지고 있는 어떤 애톰이 occupi하고 있는 사이트인데 그 아톰을 기준으로 그 아톰이 가지고 있는 substituent 두 개를 exchange 했을 때 두 개의 다른 스테레오 아이소머 안에는 이제 저희가 RS 거울상위성들체도 이제 배웠고, 그렇죠? 시스트랜스 EG 아이소머도 배웠고, 그렇죠? 두 개의 그룹을 인터체인지 했을 때 어떤 그 아이소머의 캐릭터가 인버전이 되는 에로미스틱 사이트를 저희가 스테레오 센터라고 정의를 하는 것이고, 에이시메트릭 센터는 그 정의에 의하면 스테레오 센터가 맞죠. 그렇죠? 두 개의 서브스턴트를 바꾸면 이성질체가 거울상 이성질체가 된다는 뒤에서 이제 RS 컨피그레이션을 배우겠지만 R 캐릭터가 S 캐릭터로 변하고 S 캐릭터가 R 캐릭터로 변하니까 스테레오 센터의 데피니션이 맞는 거예요. 그래서 모든 에이시메트릭 센터는 스테레오 센터다. 2. 그렇죠? 근데 반대로 모든 스테레오 센터가 에이시메트릭 센터일 필요는 없죠. 그죠? 에이시메트릭 센터는 4개의 다른 그룹이 한 카본에 붙어 있을 때 그 카본의 에이시메트릭 센터 사이트가 된다고 했는데 USP2 그리고 사이클릭 컴파운드 케이스를 보면 에이시메트릭 센터의 데피니션은 맞지가 않죠. 그렇죠? 그래서 저희가 벤 다이어그램으로 이렇게 이해할 수 있다. 어렵지 않죠, 그죠? 그래서 예를 들어서 밑에 문제 How many asymmetric centers do you have? Right? 이 분자에 대해서 asymmetric center가 되는 사이트를 세시면 되죠. 4개의 다른 사이트가 있고, 그렇죠? 한 자리밖에 없네요. 스테레오 센터는 이제 여기에 더블 본드가 있는 사이트까지 2개 더하면 되시겠죠. 그렇죠? 1개, 3개 뭐 이렇게 되겠네요. Okay, so you should be able to distinguish asymmetric center versus stereo center. Your definitions are different. Okay? So you can solve the following questions. This one you can identify one asymmetric centers and 2 additional stereogenic centers. So in total, right, this molecule has 3 right, stereogenic centers, but only 1 asymmetric centers. All right, so we'll learn about the nomenclature. So for the given enantiomer, so you can think about the molecule containing 1, right, asymmetric centers, and you can extend this idea to more complex molecule containing multiple asymmetric centers. Right? For now, you can think about one single site, one single asymmetric site, and then you can define R versus S configuration. And this is how you can call out a nomenclature of the enantiomer. Which again follow the CIP sequence rule. This is the general rule. You can first assign the priority to the substance, right? You can first think about the atomic number. And rule number 2, view the molecule away from the lowest group. Number 4, right? So you can put number 4, right? For instance, in this hatch wedge, in this case, then you can identify these 3 substitutes, right? And you can decide, right? The rotation from 1, 2, and 2, 3, right? If that will give you, right, the clockwise rotation, then you can identify this asymmetric center as R configuration. But if, right, this asymmetric center and with this 3 triangle, right, will give you the counterclockwise rotation, then you can identify this asymmetric center as S configuration. Right? So once you can, right, identify the priority 1 to 4 with respect to the central coordinate, then apply 2 and 3, you can decide whether this is R versus S configuration. This is the absolute configuration you can assign. Right? Clockwise R, counterclockwise S. Okay, so that's the only thing you should remember. This is again called the absolute configuration. Okay? So you can then practice right from this perspective formula and identify right S versus R character. Okay? And you can perhaps right decide now like priorities for substreams, right? Bromel has to be the number one priority, has the highest atom number, and you have ethyl, right? Methyl and hydrogen. Hydrogen should be the number four lowest priorities. Which you can then identify this three triangle and decide how the rotation works, right? Counterclockwise will give you S, right? And clockwise, 1, 2, 3, this will give you R configuration, right? So if right a single molecule containing one asymmetric center, right? If one has S configuration, then its enantiomer has to have R configuration, right? If you think about it. And you can apply right the way in which you draw the second enantiomer, right? Switching methyl and hydrogen, right? As I mentioned, this will give you the second enantiomer, right? That will give you then the inverted absolute configuration accordingly. Right? So in this case, you can switch methyl and hydrogen, right? That will give you the second enantiomer, right? Then the S or R character of this carbon, right? The absolute configuration will get converted to red for the right hand side, right? So it is saying this molecule has R configuration, right? Which means this has to be S configuration. Okay? 그래서 아까 second enantiomer를 쉽게 그리는 방법에서 그냥 두 개 기준 잡아서 그냥 바꾸시면 된다고 했잖아요, 그죠? enantiomer가 됐다, second enantiomer가 됐다라는 것의 의미가 그 central carbon의 absolute configuration이 바뀐다라는 것을 의미합니다. 그러니까 S 캐릭터가 R 캐릭터가 S 캐릭터로 그 작업에 의해서 변환이 된다라고 생각하실 수가 있겠죠. 여기서 한 것이 메틸과 하이드로젠이 그냥 바꾼 것뿐이에요. absolute configuration이 바뀔 수밖에 없다. 이거는 한번 머릿속에서 돌려보시면 왜 이 제너럴한 룰이 적용되는지 아마 쉽게 납득이 되실 겁니다. And you can apply this to the Fisher projections too. So we studied, right, this notation, this cross notation in Fisher projection indicate this 3D equivalent, right? So 2 and 4 is protruding out, 1 and 3 protruding in, right? And then you can apply this, right, to the RS configuration too, right? So you can identify the number 4, the lowest, right, priority substance, in this case hydrogen here and there, right? With which you can think about there's a triangle, right? The number 4 has to be located in the below, right? Protruding in from the plane, in other words, right? So you have hydrogen here at location 3, right? And then with the remnant 3, you can decide the rotation, right? The directionality, counterclockwise versus clockwise. In this case, you have chloro group, top priority, propyl and ethyl. So 1, 2, 3, which will give you, right, the clockwise rotation. That's why this is R configuration. Right? This is the opposite case. This is the natural one, right? And then you can double check though, right? This is the number 1 priority, chloro, propyl, ethyl, and this will give you the counterclockwise rotation. That's why this is the S, right? Absolute configuration of S. And you can practice this too as well, right? And one easiest way is locate, right? Interconvert, right? Where we're swapping two moieties to make, right, the number 4 priority group to the bottom, sorry, the below one, right? So you can locate, right, number 4 here, right? Then you can decide. You can make triangle from the above and decide the directionalities, the rotation. Okay? 그래서 뭐 한 가지 팁은 Fisher projection으로 주어진 스트럭처가 있다. 이걸 가지고 RS 캐릭터를 결정하시면 돼요. 그러면 앞에서 RS configuration을 저희가 정하는 가장 쉬운 뭐 일반적인 원리가 가장 low priority 그룹을 가장 뒤로 위치를 시키게 되면 나머지 3개를 가지고 삼각형을 그리실 수가 있잖아요. 그 삼각형의 이제 1, 2, 3 방향성을 가지고 RS를 정의한다고 했으니 그 원리를 그냥 이 Fisher projection에도 그대로 적용을 하셔서 뒤로 가게 배치되는 서 그룹 있잖아요. 뭐 1이나 4 정도가 이제 Fisher projection. 봅시다. 여기 1이나 3 정도가 이제 퓨처 프로젝션 상으로 봤을 때 뒤로 젖혀지는 그룹의 위치가 되니 거기에 lowest priority 그룹을 위치시키게 적당히 돌리시면 되겠죠. 돌리는 걸로 해결이 안 된다. 그러면 interchange 하십시오. interchange 하신 다음에 마지막에 캐릭터를 정하시고 다시 한번 뒤집어 주시면, 그렇죠? 그러면 원래 구조의 S 캐릭터를 얻으실 수가 있겠죠. 그 팁을 활용하시면 되겠죠. 그렇죠? 근데 나는 그렇게 할 필요 없이 그냥 이게 3D로 그냥 그려지신다. 그래서 가장 로이즈 프라이를 이렇게 머릿속으로 돌리셔서 뒤로 빼시고 나머지 3개 가지고 방향성 정하실 수 있다. 그러면 그 방법 그냥 사용하셔도 됩니다. 근데 그것보다 조금 더 난 기계적으로 접근하고 싶다. 그러면 뒤에 위치되는 피셜 프로젝션 상에 뒤에 위치되는 위치로 1번째 프라이어리 그룹이 가게 2개를 바꾸시고, 바꾼 거를 기억하셔야겠죠. 그걸 나중에 백 보정을 한번 해주셔야 돼요. 그걸 안 한 채로 그냥 어사이먼트면 이제 컨버전 된 거를 구하시게 되겠죠. 그렇죠? Okay, so that's how we can identify R versus S type of configuration in the visual projections, right? So you should remember this 3D equivalent presentation and apply the rule that we just learned. Right? I guess we can stop here and can discuss a little bit more about R and S aside next time, and then also discuss a little bit more about curve centers. We'll discuss isomer vertical curve center next time. 네, 여기까지 수업하고 다음 시간에 인사드리겠습니다.